So in this session, we will cover the role of machine learning and blockchain in wireless communication jointly. So far in the traditional talks, we have already seen the blockchain and machine learning, they are implemented separately. Whereas in wireless communication, uh, the joint implementation of blockchain and machine learning is now catching up, and there are certain advantages and disadvantages of both of them. They can be eliminated when they can come together. So in general, the machine learning integrated blockchain approach is catching up the attention of researchers in communication systems. Blockchain enhances the operation of transfer learning in sixth generation of wireless communication. There are certain limitations with machine learning, and there are certain limitations with blockchain also. So this blockchain technology can benefit machine learning, and machine learning can benefit blockchain, and together they can operate jointly to overcome each other's trouble, right? So that's what we will discuss today, that how the integrated approach of machine learning and blockchain for communication systems work, and what are the open issues, research challenges, and broader perspectives that we will discuss today, right? So if you look at this particular paper, what I've cited here, they have given a detailed overview of integrated approach between blockchain and machine learning for communication and networking systems, right? So in this integrated approach, uh, uh, they started introducing the blockchain. What is the architecture of blockchain? What's the taxonomy behind the blockchain? How it is applied in communication, networking, and system, and whatnot. And the overview of machine. They also explain the overview of machine learning, where they explain in detail about what is machine learning, the history of machine learning, and whatnot in detailed introduction, and then how they can benefit with each other, and what are the open issues, research challenges, and broader perspectives for both of them together, right? So if someone is interested, they can go through that paper and look at it. Okay, so today what we are going to cover is in detail. We will look at the integrated approach simultaneously for machine learning and blockchain together in 6G wireless networks. So as we had discussed in the last lecture, that preliminary requirements for sixth generation is ultra high data rates, improve spectrum and energy efficiency, enhance quality of service experience, and system throughput, ultra user connectivity density, and ultra low latency, high mobility, reliability. These were the preliminary requirements for sixth generation of wireless communication. So the necessity for the large data volume and supermassive connectivity imposes uh, n number of challenges on resource management, security, and privacy for sixth generation of wireless communication, right? So for that, we need intelligent, automated, decentralized, and secured approach for sixth generation of wireless communication. So that's where the solution comes across that if we employ blockchain jointly with machine learning, then the architecture becomes highly immutable, decentralized, and secured, right? So, and it can further improve the training phase of machine learning and deep learning models in a decentralized fashion. So these are the advantages. Now, quickly, if I summarize the common machine learning algorithms which are applied to communication and networking systems, they were supervised machine learning, unsupervised machine learning, semi-supervised, and reinforcement learning. So in supervised machine learning, we had the input data, which is called training data, and they have a known label, right? They have a known label. Some sort of common algorithms what we used to use is some of them are k nearest neighbors, like knn decision tree, svm for traffic classification, intrusion detection, routing optimization, even for the resource allocation also, right? And some of the unsupervised machine learning algorithms where the generic idea is the input data will not have any label, but they extract the general structures, right? One of the famous one is k-means clustering. That was the organizing map principle, principal component analysis. And there are many other unsupervised algorithms which are employed in traffic clustering, filtering algorithms, and etc. In semi-supervised machine learning, the input data is nothing but the mixture of labeled and unlabeled data, and such as, let's say, maximum likelihood learning and generative models, which we employ under this. And they were used for resource management, network behavior analysis, etc. Reinforcement learning works based on the feedback system. So whenever there is a reward or feedback, right, so that particular action is highly accepted, and if there is a penalty, that particular action is discouraged, and over the period of time system will learn or agent will learn dynamically, such as, let's say, q learning or multi-arm bandits or Markov decision process, mdp, right, is a part of this reinforcement learning. And then which is widely used in network reconfiguration, resource management, and decision making. So general flow of my machine learning model is, when we have data sources, first we train that using training sets. Definitely there would be a data processing to make it compatible with our algorithms, what we are going to implement, the code of machine learning, or uh, so that data has to be processed and make it compatible so that code can read it, and then furthermore it can extract the features. uh, Based on that, it will select the which kind of algorithm, what would be the pattern learned from that, and then it will apply the model and will do the visual analysis and take the actions according to the requirements. Now there is an advanced algorithm which is getting a lot of attention these days, which is mostly which is highly compatible with blockchain, which is called transferred learning. So in transferred learning, what happens, let's say my entire sixth generation of wireless network architecture is divided into the multiple domains. So now let's say this is my domain A, this is my domain B, and this is my domain C. Now I have some sort of resources engaged or allocated in this particular domain through a particular set of trained agents. Right? Now when I see this domain is analogous or nearby this domain, the similarity index is higher between these two domains, then in that case what I can do, I can import the learned model or trained agent from this domain to this domain, and then I can allocate the resources here without training my model separately from zero in this particular target domain. So this is called a source domain, and this is called a target domain. So similarly, this can be brought up here also based on the similarity index. But the similarity index between the domains should be, between the source domain and target domain, should be higher or larger. Then we can easily import uh, the learned model from the source domain to the target domain, right? So that's what the idea behind the target domain. Now here, the models are getting shared. So there is a breach, that could be a breach of security too, right? So to enhance the security part, blockchain could be a candidate technology which can work in coordination or jointly with machine learning or transfer learning in such, so that they can complement each other, right? So generally this is widely used in resource allocation in sixth generation of network, but there are certain limitations of this. Is first, it requires a large amount of training data, which is often not possible to get it right. So that's one trouble. And now another one is the computational capability is is difficult to get this kind of machine learning algorithm. That's why the centralized architecture is not preferred. Decentralized architecture is even a better and preferred one. Accessing and aggregating a large number of data for training is definitely a challenge. So we cannot proceed with that. So that's why the distributed machine learning architecture is highly preferred one. But inefficient management of data sharing will lead to the security and privacy preservation issues, right? So that's the major trouble what comes across here. And because when we share the personal information of the clients through sharing the learned models, there would be privacy concerns, correct? So that's why centralized architecture is heavily prone to the hacking and other things, or maybe when sharing also it may create a trouble. So that's why the blockchain technology comes under the picture to overcome this. Even during the transferred learning, when we share the model, that could be a chance of breach of securities, right? So that's why the blockchain comes across the picture, that can help us to improve the security. So generally, if I look at the blockchain, right, so there are three major components. One is cryptographic components such as hash functions or digital signatures to preserve the client's information in a secured fashion. So generally, SHA 256 is widely employed algorithm. There would be consensus protocols, the principle and paradigms of distributed systems. There are various consensus protocols we will discuss in a soon, in a while, and there are separate blockchain structures, different types of blockchains that we will discuss, and the smart contract theory that we will discuss soon, right? So if I start, the concept that what is blockchain, right? So the blockchain is nothing but a distributed ledger that involves a set of immutable transactions among the untrusted parties without any centralized controller or human intervention. So it's kind of a, whenever new resource is allocated or new transaction happens, all the miners will try to mine it, and whoever is successful, he will add a block into the chain for a newly added transaction, and then that block would be broadcasted. I mean, that chain would be broadcasted across all the nodes, so everyone will have a copy with that new transaction. So the transaction on a blockchain are grouped and stored, and they are immutable, they are tamper proofed, because that ledger is distributed, and all the nodes in the network will have a copy of them. So they are tamper proofed, right? And each of them is verified by using the consensus mechanism before they can add it in a chain, right? So it's kind of a decentralized governance here completely. The basic idea behind this is decentralization, transparency, immutability, higher security, auditability, and no, I mean autonomy, correct? So the basic idea of the blockchain is, let's say, if I take a bank's example, so it would be a centralized ledger, right? So in a bank example, if I see, there would be a centralized ledger. So bank will hold the golden record. Everything would be registered by the bank. And if there are, let's say, a client B has some sort of discrepancy in his records in the transaction, he has to go to the bank and convince the bank that there is a discrepancy in my observation of the transaction. And then if the bank is convinced, then it would be restored for a client, right? So there is a middleman here. Whereas if I look at the distributed ledger, where there are multiple nodes, where distributed ledger, if I see, there are multiple nodes, and now there is a single distributed ledger which is getting accessed by all of those, and they have a consensus protocol. So once all the nodes agree using a consensus protocol, then and only the new transaction will be added, and everyone will have a copy of it. So no need to have a central middleman, and none of them is going to the central middleman. So it's a complete decentralized architecture, whereas this is a complete centralized architecture. So that's the advantage of a blockchain technology. How it works? So let's say if any transaction occurs between two people, right? Any transaction occurs between two people, it's going to be hashed and broadcasted uh, to the all the nodes. So let's say that this transaction is happened between these two people. In the context of wireless communication, that could be a resource allocation between these two, and this can be mapped in a block, and a new block can be added in the chain, and a new block can be added in a chain, and it could be stored, grouped into a block of special nodes, right? So, and that would be broadcasted across all the nodes, and that would be broadcasted across all the nodes, right? So this is how it would be stored. Now the idea is, it's a shared ledger, so everyone knows a copy. If someone tries to steal or tamper it and uh, alter it, then everyone will have a copy, so it would immediately be detected that someone is trying to tamper. So that's the idea of a blockchain. So let's say, generally, each block will include the number of transactions at that particular time which have been linked, and then it will consider a previous hash of the block. So let's say, this is, let's say, existing block, okay? So the previous hash of the block is, what is hash of the block? We'll see. Maybe a code of that, right? So previous hash of the block is stored in the current newly added block, and then the current block's hash would also be stored, and here is the detail of all the transactions, and then it becomes a chain of all the blocks. That's how it frames a blockchain, right? So blockchain approach is nothing but a shared ledger which will record all the transactions. Blockchain is nothing but a shared ledger which will record all the transactions, and it will share across all the nodes, all the participants. So everyone will be able to see that, right? So they have a replication. I mean, they have a copy of it. So generally it could be an open ended blockchain, then in that case everyone will be able to see, or it could be a private blockchain also that everyone cannot see, but it can be seen by the permission, right? So if someone wants to take a look, then he has to ask for a permission, and if the permission is granted, that person or a node can see the block inside the chain very easily. So the shared system for a record, the idea behind of this is kind of an increased security and eliminate the middleman. So it becomes completely a decentralized structure, eliminating the middleman, right? So for this, adding a new block, we need a consensus protocol. So before we add any new block in the chain, there is a common agreement between all the nodes or participating nodes, which are, if they all of them they agree, then in that case only a new block will be added into the chain, otherwise it won't be added into the chain. So they have to come up with a common agreement. And so that's how. So there are some of them, such as consensus protocol, let's say proof of work, proof of stake, or proof of activity, or practical Byzantine fault tolerance based one. There are many of those. So some of them are, the famous one is like proof of work and proof of stake. They are very famous one. PBFT is also very famous one, right? So we will just look at the proof of work. First, we will look at few consensus algorithms, and then we will move it. So first one is proof of work. Okay. So first one is proof of work. So in this, if you look, proof of work, proof of work is widely used to confirm the transaction and produce a new block to a chain by giving the proof of the previous work, right? So the more a miner, it has more completed jobs, and based on that, it gets more experience. So kind of a proof of work, right? So miner, when he complete against each other, so miner means what? I mean, see, whenever the new block has to come, it has to the participants must find a solution to a hashed puzzle for a block proposal. So any new transaction comes, all the miners will start solving a puzzle sort of thing. And as soon as a particular node solves that puzzle or a problem or answer to the shared question, then after that it goes to the verification across all the nodes based on that POW concept of or consensus protocol. And then once everyone agrees, a new block would be added proposed by a particular miner recording the transaction. That's the general protocol of a proof of work. So uh, let's say there are some sort of puzzles given, right? So solving some sort of cryptographic problems or complex mathematical problems. Let's say if this block 22 is having a puzzle number E, G, and I, right? And there are three miners. Let's say miner 1, miner 2, miner 3. And let's say this node 433, he's capable of solving this new puzzle, and he has solved it across these two, right? But he has solved it, so his block would go to the proposal of the consensus through the consensus protocol. When all the nodes agree, and then it will say, okay, this miner has solved the problem, cryptographic problem, and we are going to add this block, which is added by this particular miner, and this is now getting framed a chain, blockchain. This is going to be broadcasted across all the nodes, 281, 722, some sort of node IDs, 433, correct? These are all the nodes. And then they will agree, okay, that person has solved it, and we allow them to put a block in a chain. So that's the general idea of proof of work. Now, sometimes the problem comes of forking. So here what happens, let's say, if there are, a fork is generally a creation of ongoing alternate version of the blockchain by creating two blocks simultaneously. If two miners can compete, and if they come up and solve that problem simultaneously at the same time, come up with a solution. Now there is a problem. They may create two parallel blockchains. One will start adding the blocks here, one will start adding the blocks here, right? So that's called forks, right? So they will split up, and then they will start two blockchains because they solved. So let's say this miner has solved, it has added block here. This miner has also solved, and after the mining, they have solved two separate blocks, and they have added them. So it's called now two separate blockchains, or two wings are created. So now New blocks will be either padded here or here. So now that's called the forking trouble, right? So that we have to avoid smartly. Now, if we look at proof of work and proof of stake, correct? So proof of work is generally the probability of mining a block is dependent on how much work is done by the miner previously. So let's say whenever we go for a job, right? So whenever we go for a job, so generally they'll ask for our experience, how many years we experience we have. Let's say 5 years experience, 10 years experience. The larger is the experience, we get a better job. Generally straightforward equation, right? So that is called a proof of work. Whereas proof of stake, correct? Proof of stake is something different. It says you can mine depending on how many coins they hold, right? So maybe correct, it depends on how many coins he holds. It doesn't depend on the experience. It depends on how many coins or one person holds. So this is called proof of stake here, right? This is called proof of stake here. Now if I look at two types of the blockchain, there are three major types of the blockchain. One is private blockchain, one is public blockchain, and another one is consortium or federated blockchain, which is nothing but the somewhere in between the private and public blockchain. The idea behind a public blockchain is a permissionless blockchain where there is no permission required. When someone wants to access a block within the chain, or someone wants to see the entire blockchain, it's open. There is no permission required. An open network system where all the devices can freely access without any kind of permission. So ledger is shared and transparent completely. Okay, so whereas in permission blockchain, uh, when someone wants to take a look at a blockchain, he has to take a permission, or a node has to acquire a permission from the competent authority. And then once the permission is granted, he can see that. That is the idea of a permission blockchain. So if we look at the public blockchain, they are permissionless, and anyone can join and participate in the network freely, and all the transactions are open, completely open, right? The public blockchain can send, receive, check, verify the transaction, participated in the process of consensus, anything. In a public blockchain, right, publishing new block usually needs either. No, but the problem is it's kind of computationally expensive because it's open, but it takes it is computationally expensive. And second one is uh, you need a lot of I mean it takes a lot of time to come up with it. So that's the trouble with it, right? So whereas in private blockchain, it is private, and you need a permission, but private blockchain provides better feasibility and way for some groups and participants sharing and verifying the transition internally. Since the blocks are published by delegated nodes within the network, some of the rules or data could be modified and tempered. I mean, that's trouble here, because see, when it is private, some of the nodes can alter some of the items, and they can convince other people that okay, I'm altering, let's frame a group and you support me. So it's kind of an hacking attack sort of thing. Whereas in public blockchain, it's open to everyone. So hacking is difficult because this prevents everyone is knowing everything, so it's difficult to temper that. Whereas in private, we can public people can frame a group and then create a trouble. Now that's why to eliminate the disadvantages of them to eliminate the disadvantages of them, the intermediate way came, that is a consortium or federated blockchain, which is usually operated by a group of pre-selected node, right? So some sort of competent authorized blocks are given, and they would be operating uh, but as a pre-selected node, they would be operating the entire structure. So all the nodes, they do not have the authority to send, receive, check, verify the transactions in this type of blockchains. But the selected nodes they have, the trusted nodes they have. So somehow it is in between the public and private blockchain. So just to ensure that the computational complexity is lower, plus just to ensure that the security is also at a decent level, right? So, and the consensus protocol may be operated by some pre-authorized node instead of all the nodes. So that's why it's not computationally expensive, and it's somewhere in between public and private with a decent security. Correct. Now, the next terminology is called the smart contract. In the smart contract, what happens is, let's say I'm ordering something on a Flipkart, correct? So let's say the payment first it's get deducted, and then XYZ company will deliver the item. I mean, let's say the Flipkart delivers me the item, or maybe any e-commercial site will deliver me the item, and then after there is an intermediate body. After that, it is having a smart contract. It will release the payment completely to Flipkart, right? So this entire contract is automated. So it's simply a program generally stored on a blockchain that will run when the predetermined conditions are met. So let's say the transaction, there's the money is paid, then and only then the item it's getting delivered. So it's kind of a if, when, and then sort of things, and then it will execute the transaction. It will execute the actions when permitted conditions are met, and once the transaction is complete, correct, and item is delivered, it cannot be changed. It will be stored in a block, and it will be added in a chain, and then it will stay there. So these are called the smart contracts. Benefit of the smart contracts are is once a condition is met, and the contract is executed and then the contract will be executed immediately, right? Because the smart contracts are digital and automated, so there is no paperwork or process or anything. So it's going to be executed immediately. The idea of the smart contract is to establish the trust and transparency. So no third party is involved in that. So the idea is like, it's transparent and it's known by everyone, so the authenticity is higher because it will be stored in the chain. And then they have the encrypted records, so highly encrypted records, these algorithms would be used, and because of that, encryption security is also very high, and it will save a lot of efforts by removing the intermediaries. The time delay is saved, computational complexity is also getting saved, right? Now the privacy, how it comes. Ledger is shared, correct, but participants, they require privacy, right? So ledger is shared, but we should not disclose the information about the participants. That's why we use highly cryptographic algorithms such as SHA-256 to overcome this, where we used to convert the identity of a user in the form of what we call code or some sort of thing. So it becomes very private there. So the transactions will be private, identity will not be disclosed, and transaction need to be authenticated, right? So that's why. So the cryptographic hash functions or digital signatures will be generally used. So there are two main cryptographic concepts in blockchain. One is hashing, another one is digital signature, correct? So we will take a look at the generally. This is kind of a symmetric cryptography, asymmetric cryptography. In symmetric cryptography, what it does is, like, both of them, they have the same key. When I transmit, receiver will have a same key. It has to open it, and then it can see the message. Whereas asymmetric cryptography or asymmetric encryption, there will be one public key there that is used to broadcast the message, and each access point who wants to see the message, they will use their own private key, and then they will be able to see the message. So this is called asymmetric cryptography, right? Now we will see this sort of how are we doing this, that we will take a look. I am on this blockchain demo portal. So here you can see SHA-256 is nothing but secure hash algorithm. So if I type any message here, let's say hello, right? So it will give me the hash of this. So this is, you can see the very long coded message. You can see the hash, right? So I mean, it's very difficult to detect it, what I have written here in the data, correct? That's what 256 algorithm does. Give me a highly secured hash key. Now this hash key will be added here when framing a block, right? So this is my block structure, one block. This is my one block, right? So this will be added here when I create a block here. So this is my block number one, right? And let's say some sort of message, hello, right? And then miner, when I click on it, it will start mining. Now it has solved the cryptographic puzzles. It will automatically generate some sort of cryptographic puzzles to encode this information or transaction here using the hash key and SHA-256, and it has mined it. So the moment when it became green, it has mined it, and now what it does is it's going to add it in a chain. It's going to add it in a chain. So now let's say with reference to wireless communication, how we do this. Okay, let's see with reference to wireless communication, how we do this. So simple algorithm we will take here, just the booking, resource allocation booking. Okay, just the resource allocation booking we will discuss here. So here you can see, let's say I want to start a communication between node number 21, which is here, to destination node number 5, which is here, with a data rate of 1 Gbps and with reserved BER of 10 power minus 12. So I want to establish a connection between these two and book these resources, right? So what am I going to do here is I'll go to the block of that particular one, right? I'll go to the block of that particular one. Let's book it. So this is resource of block number 1. So I'll go to the blockchain. So now here you can see, you can create the blockchain. See, we can use a Python also. That is also okay. Where we can write the raw codes and other things. So block number 1 tells me that I want to talk between node number 21 to node number 5 at data rate of 1 Gbps. Now this is the first block, so there is no previous hash here. Okay, this first hash is this one only. That's the first block. When I mine it, so I'm mining it. After a few seconds or maybe a fraction of time, the miner has solved the cryptographic puzzle, and then see, you can see the block is converted into the green color. So now we can see this block is added in the chain. Okay, so now once the block is added in the chain, everyone will be able to see that node number 21 is talking to number 5, because that blockchain is broadcasted across this domain, right? Everyone will be able to see that node number 21 is talking to node number 5 for so and so data rate, so and so B. Here you can write the frequencies also here, right? Let's say f equals to maybe 28 gigahertz to 28.1 gigahertz. So that is also okay. That is also possible. And then everyone will have a copy of this block. After some time, right? Let's say now node 7 wants to talk to node number 12. Node 7 wants to talk to node number 12. So now what it does, it will avoid this range of frequencies here. Let me add the frequencies also. Let's say f is equals to 28 to 28.1, right, gigahertz, 5G frequencies, and let's mine and edit here. Correct. So that would have helped me. So I'm just mining it again, right? So here now, let's say this new block, what we want here. So see, now second block is requesting a resource between node number 7 and node number 12. When this block occurs, it has to avoid these two frequencies. So it will see 28 to 28.1 is being used already. So I'll use 28.1 or maybe 28.2. I'll leave a little bit of guard between to 28.3 gigahertz, correct? So you can see I have, and then I'll send it for a mining. And then as soon as it is solving the cryptographic puzzle, it will solve. Once it is solving the mathematical puzzle, it will be added in the blockchain, right? Blockchain. So now you can see this block has been mined and it is added here. Now, if you look at this carefully, this is my previous hash of a first block, which is directly placed here. You can see the code is exactly same. 4 zeros, 4 zeros, BD, BD, 50, 50, right? And this is my current hash with reference to this resource. As soon as this engagement occurs, all the nodes will get a copy of a blockchain, and then everyone knows that 7 is talking to 12 at with this parameter at maybe 28.3 to 28.4 gigahertz. So that's called a resource blocking. So this is how the chain is created for the resource engagements, right? For resource allocation. This is your block number 0, then this is your block number 1. This is the current hash based on the booking of the current resources, and this is my previous hash of the block. Similarly, it propagates, and then the entire chain is created accordingly. Okay, the entire chain is created accordingly, right? So this is how we have just created now, and you can go through this site always for creating the blockchains. There, you can give a try. So now this is how we have added the blocks. This is how we have added the blocks in the chain. So each and every block would be mined, and then it would be added subsequently. So this is how the resource engagement can occur, or resource allocation can occur through the blockchain, right? There is no machine learning yet. This was just purely based on the blockchain. People used to write the Python codes or maybe Solidity or Vipers, right, to do this kind of things for the resource allocation and wireless communication. But there is nothing much has been done so far. But this is kind of a catching up very quickly across the research community. So if someone is looking into this kind of work, this is a good time to start. So there are 9 fundamental modules of the blockchain architecture. First one is the identity management. Okay, so how to create, control, and operate identity of the participants. We cannot close them, so that's why we use the SHA 256 to keep the identity hidden, so no one can see who is the participant, right? Because it's going to be shared, so definitely everyone can see. So we have to ensure that the security is not compromised here. And program development, how it works, and then what is the information propagation, how the block is proposed. Block verification is also important. Block confirmation is also important. And who can access the block? How are we going to store the block chains? Those memory issues and all these nine fundamental problems have to be addressed in this. Now, the integration of blockchain with reference to 5G and beyond, that is something important to discuss. So there are certain benefits of decentralization with blockchain, correct? So the benefits are the security with decentralized trust is very high. It's very good. And it's an autonomous and flexible system for the smart contracts, which preserve higher privacy and security using the cryptographic technology, right? And this is very suitable for dynamic resource sharing, where we are using transferred learning or decentralized system, right? So this will help us to improve the security a lot. That's why the coordination of blockchain with machine learning is very important. The advantages what blockchain brings for for wireless communication systems is, first is it's decentralized. There is no central controller, so the computational complexity would go down, right? So, and that is a mostly expected behavior with the transferred learning. So that's why the joint work between transferred learning and blockchain can substantially improve the performance of each other. It is highly transparent because all the nodes will have a copy of a blockchain. So it's more credible, because if someone tries to temper it, alter it, change it, it's, I mean, people cannot, I mean, everyone has a copy, so it will immediately differ, and then people will be able to detect someone is trying to alter it. And it's not easily reversible. So it's technically it's irreversible. Once the block is added, it's one-way cryptographic hash functions. If it has to change, a person has to do a lot of effort. So it's nearby irreversible thing. Okay, so the security is very high for the blockchain. Auditability, autonomy, and pseudonymity is very high. Pseudonymity, that means each node will interact with a generated pseudonymous address, so the privacy is high. Node's identity will not be disclosed or compromised at any cost, right? So these are the several advantages of my blockchain technology. However, there are limitations of blockchain, right? There are limitations of blockchain. First one is the consensus protocol. They consume huge energy in validating and sharing the transactions on the blockchain, right? It consumes a huge energy in validating and sharing the transaction on blockchain. That's the very heavy bottleneck. And the cryptographic hashing functions, hashing process of adding each and every block is computationally very intensive when we add cryptographic hashing, right? So this computationally it's very intensive, and it consumes huge energy. Right? So to create each block, miner needs to solve a puzzles that will consume a lot of energy. Adding too many blocks, so let's say if it's a dynamic atmosphere and if there are a lot of blocks to be added there, then again it's going to create a lot of memory issues, maintaining the long blockchains and other things, right? That's why the scalability is another question, because when the transactions are very large in number with ever increasing number of transactions, correct? So scalability is the issue, and would occur a bottleneck, and it will consume huge energy resources. Now, how we overcome them? That's why the machine learning comes into the picture and help blockchain to overcome those issues. Machine learning can make smart contracts even more smarter. It can optimize the performance of the blockchain by improving the energy, reducing the energy consumption, and establishing a resource efficiency. It can work intelligently on the scalability part, so that it doesn't consume a very large memory or computational capability, or cut down the energy consumption also, right? And simultaneously, it will increase the security also. Now, how the blockchain can benefit machine learning, such as when we share the training models or transfer learning, security is at a cost. It can be compromised. At this point, blockchain can help to overcome this problem with machine learning, and then it can increase the security and privacy, right? In a decentralized structure, with a trusted decision making methodology, right? So if you look at this, blockchain can benefit machine learning for data and model sharing. So here you can see this was my centralized structure with a central controller, and this is my decentralized structure, correct? So where data can be shared over, when there is a centralized ML, generally everything comes to the center, and centralized architecture where central server will process and control the data using large storage computing resources, correct? Whereas in distributed network, generally the architecture is in such where a central controller controls the process for training and model, but the distributed users will train the model, right? So that is somewhere in between. Centralized control will control, but the models are trained distributedly. Whereas in decentralized blockchain-based architecture, everything is decentralized without any central controller, and where the controller for data and models are completely driven in a decentralized manner, right? So decentralized blockchain-based machine learning architecture without any central controller for data and model sharing, right? So if I look at the blockchains, a feature of blockchains which will benefit machine learning, so generally it is shared, transparent, and distributed ledger, which is immutable, irreversible, and auditable, which is secured by cryptographic secure digital ledger, and this all benefits will come with to the machine learning in the form of data model and sharing. It will improve the security and privacy. It will enable the decentralized structure so that computational capability goes down, and trust and decision making skills are also improved here, right? So, and then directly it can scale up towards the wireless communication. Now, blockchain can benefit machine learning, specifically when training the machine learning models. Usually they require number of data. I mean, they require a large number of data generated by multiple entities, which may increase the privacy concerns. Right. So, to eliminate the privacy and security issues, blockchain will substantially help machine learning algorithms when specifically it is a shared architecture such as transfer learning, where pseudonymous addresses will be used to avoid the identity exposure, and cryptographic algorithms definitely will secure the data, or model sharing, maintaining the higher or larger security or privacy things when it comes to the machine learning part. Now, simultaneously, machine learning can help blockchain substantially in multiple ways. As we discussed, the blockchain is a shared ledger. Everyone will get a copy. And when the dynamic atmosphere is there, there are, let's say, thousands of, or maybe even more large number of blocks are getting added very rapidly. That is highly energy consuming process. Resource efficiency won't be there when the scalability is on a is on a question, right? And that's that's where the machine learning can optimize the performance of blockchain in such a way, or operation of blockchain in such a way, so it becomes more and more intelligent, cut down the energy consumption, cut down the resource computations, right? Using the machine learning or deep learning algorithms. That's how it will address the scalability issue also in machine learning or deep learning, machine learning and deep learning, right? So th- that's how both of them, they'll complement each other. So machine learning can benefit blockchain, blockchain can benefit machine learning. Both of them work together to accomplish the common objectives of sixth generation and beyond of that communication systems. Correct. So more mainly, blockchain can benefit machine learning. Blockchain can benefit machine learning through data and model sharing, for security and privacy, for achieving the decentralized structure, achieving the trusted decision making, whereas machine learning can help blockchain through energy and resource efficiency, addressing the scalability issues, improving the smarter contract, make it or more make it more smarter even, and accomplish the resource allocation or any other task in 5G or sixth generation of wireless communication network, right? So, however, there are certain open issues, research challenges, and broader perspectives, right? Where the integration of blockchain. Now, the first open issue is how will we integrate blockchain and machine learning in communication systems? That's the first major question which people are not, I mean, people are trying to address it, right? So, it's an open research problem. The interoperability is difficult when I mean the blockchain and machine learning algorithms or machine learning communication systems, they have to talk to each other. Uh, we have to identify efficient consensus protocol applying the machine learning, right? So the current consensus protocol can be even more smarter, or it can be optimized further using the machine learning or deep learning further. Decentralization, sometimes, I mean, there is always a debate uh, between centralized or decentralized structure. I mean, there is always a debate. People say centralized is better, decentralized structure is better. Some of them say the hybrid version is better. So, and this is always an open issue. How are we going to enhance security and privacy jointly when we have that? We have to test and prove that simultaneous work between machine learning and blockchain jointly can improve the security and privacy. How the data and model sharing is happening, how the resource management will happen, how are we going to save energy, how are we going to address the scalability issue. So that's all I have for this particular session.